In this video, we're going to discuss the different states of matter that are possible for all substances. This is a topic you probably covered in science classes prior to now, but we're going to go into a little more detail than you've probably seen in the past. We'll start with a quick rundown of the learning objectives of this video. The first part of the video will be discussing the actual states of matter themselves, what are their basic definitions and characteristics, and most importantly, we'll take some time to compare the three different states of matter that we'll be working with so we can see how they are similar, yet how they are also different. We'll also take a little bit of time to discuss the fourth state of matter. It's something that comes up every now and then, but people tend to not know a whole lot about it. That fourth state of matter being plasmas. We have a couple quick definitions as to what a plasma is and where you might see it in the world around you and in the universe as a whole. We'll then move into something we'll cover in a lot more detail later in the chapter, the concept of intra and intermolecular forces. These are forces that exist inside a molecule and also between different molecules and govern a lot of the behavior those chemicals actually have. Last but not least, you can't talk about states of matter without also discussing the concept of state changes, going from one state to the other. Turns out there happens to be 6 of these state changes, although most people are only aware of a couple of them. We'll see these state changes in the context of something known as a phase diagram. This is basically a graph that shows the pressure-temperature relationship and all the temperatures and pressures that these state changes occur at. Before we plow ahead, just to give you a quick example of what we're kind of getting into, we can talk about some different states in terms of some of our elements. One of the more uncommon elements would be mercury. This is a metal that exists at liquid state at room temperature. It's something that most people know about, but not all people have a lot of experience because it is a fairly toxic substance. Just like any other substance, by changing temperatures and pressures, we can get liquid mercury to turn into a different state. In this case, it would be solid mercury. In this situation, a cryogenic fluid such as liquid nitrogen was used to cool the mercury to a point where it solidified, and these scientists molded it into the shape of a small fish. As the temperature would start rising again, we could get this state in the solid state to turn back into the liquid state, and we can see that process of the state change in this case, which would be melting. This video is all about clarifying a lot of these processes and making sure that you're familiar with what's going on in each different scenario. As I said before, we'll start with a quick introduction and basic definitions of the different states of matter. The first state of matter we'll talk about would be a solid state of matter. This is a state of matter typically found at lower temperatures, and the key thing that makes a solid different than everything else is the fact that they have a fixed shape and a fixed volume. When you make something into a solid, it stays that way. The picture on the left shows an example of a solid. This is a crystal of the element bismuth, known for making these very peculiar rectangular structures and these very vivid colors. The next state in line is going to be the state being liquid. This is a state of matter typically found at intermediate temperatures, still has a fixed volume like solids do, but in this scenario adopts the shape of its container, so it does not have a fixed shape. For all of us who have been around liquids all our lives, this is something we're very familiar with. Again, looking at the picture on the left, the liquid we're seeing here is one of the few liquids that shows up on the periodic table. We saw mercury a few minutes ago. Here we're looking at liquid bromine. You can see it's a liquid with a boiling point very close to room temperature, meaning we also expect to see a lot of gas going along with this. Continuing our trek through the different states of matter, the next state of matter we'll talk about is going to be gases, and this is where we're going to spend the majority of time in this chapter talking about. This is a state of matter typically found at higher temperatures, and in gases, we kind of continue the process here. Gases take on the shape and the volume of their container, so they have no fixed shape and they have no fixed volume. So gases pretty much occupy whatever it is they're placed in. Again, over on the left, we have a picture of a green-yellow gas here. This is the gas chlorine, something very, very toxic, very, very caustic, and one of the first chemical weapons used back, I think, in World War I. Last but not least, and we'll talk about this a little more in a minute, the fourth and most mysterious state of matter, plasma. This is a state of matter that's typically found at very, very high temperatures, things like the sun, for example. And by its temperatures are so high, there's enough energy around to actually pull electrons off of the actual atoms themselves, and what you kind of get is this sea of ions, basically, these charged atoms or these naked nuclei with these electrons freely floating around them, making these things behave very similarly to metals. On the left again we have a picture. This is a picture of the inside of a device known as a tokamak, which uses very strong magnetic fields to hold and maintain a stream of plasma. This is one of the earliest technologies used for coming up with nuclear fusion power. So it's something that's kind of in cutting edge research. But plasmas have a lot of much more mundane applications we'll talk about a little later. Let's start this process of a comparison. I think before you go too much further, you should take a minute and draw some quick sketches of the pictures we have here. A lot of times these pictures are available online, maybe not these exact ones, but you'll find something very similar. What we're really trying to do here is compare and contrast at an atomic level what's happening in solids and liquids and gases, and then try and relate that back to some of the definitions we just saw. So in solids, the big characteristic here is that you've got very closely packed molecules, and notice those molecules form very regular recurring patterns, and that's something we'll be looking at in terms of solids. This is one of the things that explains the fact why solids have a fixed volume. They're already as close together as they can be, you can't squeeze them or anything like that, and why they have a fixed shape. That regularly recurring pattern means there's a lattice to this, and that lattice maintains the shape of your substance. We can then move over here to liquids in the next picture. We notice liquids are also very closely packed together, which means, again, they have their own fixed volume, but what you'll notice is the big change here is that liquids do not have that same regularly recurring pattern. These guys are pretty randomly distributed, which is why, without that structure, liquids don't have a fixed shape. They adopt the shape of the container that they're in. Last but not least, and here's what you'll notice, and this is, by the way, why we treat these things differently, there's a big kind of break right here. Solids and liquids are actually relatively comparable to one another and behave in similar ways. Gases are very, very different. Notice the particles are much more spaced apart, and this, by the way, is not nearly exaggerated enough. They're much more spaced apart than this, and they're moving at much, much higher velocities. As a result, these gas particles can get bigger or expand, or they can contract the space they're in, and they will ultimately not have a volume. They'll match the volume of their container, and they also don't have the shape because they lack that structure. But again, I think the best thing you can notice from this, again, is the difference between solids and liquids on one side and gases on the other. We treat the gas part of the chapter separately. It's got its own set of rules, and then solids and liquids will treat together as a group with their own set of rules. Now let's see if we can't put some of this together onto a little chart here that's going to kind of summarize some of these similarities and differences that go along with solids and liquids. So for solids, we can say things like they have a definite shape and volume. So that's one thing you can do here. Liquids have a definite volume, but no definite shape. And gases don't have any of these things. Gases basically adopt the shape and volume of their container. So definite shapes and volumes here, definite volume, but we can say here we adopt the shape of our container. And then finally gases do neither of those. So that's one thing we can say there. Something else we can add onto our list to kind of get along with the process a little more. Solids generally are relatively slow moving atoms. Atoms and molecules in solid are relatively stuck in place. Liquids have a relatively slow to medium velocity, whereas gases have very high velocities. So we have a very high velocities for the gas, and we're talking literally hundreds of meters every second the velocity that the gas particle is traveling at. Moving on with our list, we can talk about the fact that solids we would describe as being non-compressible. This goes along with the concept of definitive shape. If we press on a solid, it generally stays the same exact volume that it has. We can't squish these. Liquids we would also describe as being non-compressible, whereas gases are the other way around. These are indeed compressible. Something that's taken advantage of in a lot of different applications, for example, storing gases in tanks under pressure, storing gases in tanks in order to use that pressure to expel things like an aerosol can. Lots of different things take advantage of the fact that we can compress gases and as a result store energy. And last but not least in our list, we can again go back to the page we saw just previous with the diagrams on it. We would describe again the molecules or atoms in solids as being very closely packed. atoms. We would say in liquids they are also very closely packed, whereas in gases our atoms are very spread apart. Now this is not a comprehensive list of everything we could possibly say about solids and liquids and gases and their similarities, but it kind of gives you an idea, or at least a start, trying to think about these things as being how they're matched together and also how they're very different. Before we plow ahead and get into some of the more important stuff in the chapter, I do like to take a minute and talk about the fourth state of matter that doesn't always get a lot of attention, and that's going to be plasmas. So let's go over a couple quick ideas with plasmas. This is not the kind of thing I expect you guys to do too much with on tests or quizzes, but it is something I think you're least familiar with, and also people tend to have a lot of curiosity about this. Plasmas, again, as we said, occur when when enough energy is added to a gas to ionize those atoms, in a sense, remove the electrons, and then to keep them in the ionized form, meaning there is a continuous supply of energy that keeps things going. Atoms or plasmas, when you make them, tend to need to be ignited. You get a high enough temperature, usually you apply something like a spark or something like that, and that kicks off a process where this ionization happens and it maintains itself in the plasma state. As a result of having all these ions present, this gives a lot of conduits for electrons to travel through, meaning that plasmas conduct electricity very similarly to metals do. And this is one of the characteristics of plasma that get exploited in a lot of different venues. Turns out, and this is the strangest thing about this, that plasma, despite the fact that we think it's so rare, is actually the most common state of matter in the universe. Most matter in our universe is in the plasma state. Some quick examples of stuff you might see on our planet that examples plasmas. Neon signs. The colored gas you see inside of a neon sign actually is that gas in a plasma state. The flames we see in a fire, people often ask what those flames are actually made of. It is the atmospheric gases we have around us that are heated to a point where they turn into plasmas. Likewise, fluorescent light bulbs also have plasmas. And have you ever seen one of those spheres that you can get at like science centers that have those like lightning bolts going inside? Those again are examples of plasmas. The reason plasmas are the most abundant substance in the surface is because of this stuff right here. All stars are formed up and made almost entirely of plasmas, and since they are the largest objects in our solar system, or in our universe I should say, they tend to harbor the most amount of matter. Now, as you can see in the video playing right now, we're going to give an example of the fact that gases, or plasmas I should say, do indeed conduct electricity because of these charged states. What you see in front of you is a candle. That candle is held between two magnetic plates, and as these plates are charged, what's happening is they're increasing the voltage, increasing the electrical potential throughout time. What we can start to see happening about now is the fact that the candle flame is starting to get attracted to the magnetic plates. Again, these are the positive and negative ions that are created in our plasma being attracted to the opposite plate. The positive ions are moving towards the negative plate, the negative ions are moving toward the positive. Towards the end of the video, we can start to see now that the electricity that's charged between these two plates, while it couldn't arc across the plates before, is now using the charged ions in the gases to arc between the two plates. And as a result, we can see that these gases, and these plasmas I should say, again are conducting electricity better than the air around it. Alright, let's change gears again back towards things that I think are a little more pertinent. These are things you do need to be are held responsible for, so if you weren't taking notes on the previous slide, you need to get back into gear. We're going to start talking about the different types of forces that exist within and between molecules. The first on our list will be something known as intramolecular forces, and you're going to find in a moment that these words are very similar. You're going to have to be very careful and very aware of the fact of the subtle differences. So now we're talking about intramolecular forces. These are forces acting between atoms, and the key point here is within a single compound. So these are the forces inside of a molecule. Some simple examples of these: the forces holding ionic bonds together would be described as intramolecular forces. The forces forcing atoms to share a pair of electrons and holding them together would be intramolecular forces. And as we start getting into larger molecules with big long chains, like say for example proteins in your body, these molecules fold in on themselves, and one part of the molecule can be attracted to another part of the molecule, holding that molecule together. If you recall, proteins have a very specific folding pattern, and that folding pattern is determined by intramolecular forces. The other force we'll be dealing with, which is something a little more related to what we're going to be working on in this chapter, is the sense of the idea of intermolecular forces. Intra means within, inter means between. These are forces acting between different molecules in a sample. So one molecule being attracted or repelled to another. And these forces, as we'll talk about later in the chapter, are typically electromagnetic. And the strength of these forces is a big determining factor for the chemistry that these substances go along with. Focusing a little more in depth on the intermolecular forces, intermolecular forces tend to be stronger when the molecules are closer together. If you remember Coulomb's law, one of the big factors is distance, and those electromagnetic forces get weaker over distance. Now what this means for us is that there are lots of intermolecular forces in solids and liquids. Those atoms, as we just saw, are very close together, and those intermolecular forces play a large role in the behavior of solids and liquids. Likewise, there is very little intermolecular force in gases. Those molecules are far apart, the forces are relatively weak, and as we'll talk about down the road, we can usually ignore them. The strength of these intermolecular forces, aside from distance, is determined by the characteristics of the molecules themselves. As we'll talk about later in the chapter, these characteristics can be the size of the molecule, can determine how big intermolecular forces are, and more importantly, the polarity of the molecules. Polar molecules are naturally electromagnetically attracted and repelled from other polar molecules, and that's going to account for the majority of our intermolecular forces. Last but not least, more and stronger intermolecular forces again impact the behavior of our substances. Things that have more and stronger intermolecular forces are more likely to be a solid. There are a lot of forces holding things together, and if you remember, that's what solid were. What? All the atoms being held together. Likewise, more intermolecular forces means it is harder to melt or boil this substance. Melting and boiling means pulling the atoms and molecules apart from one another, and that's going to cause us to have to overcome those intermolecular forces. This will mean higher melting and boiling points. Again, though, we'll cover all of this in more detail later in the chapter. All right, last but not least, we're going to wrap this video up by a quick discussion of the concept of state changes. Basically, a state change occurs when the conditions of a sample are changed, causing it to change from one state to another, solid to liquid, liquid to gas, etc., etc. And these conditions that we're talking about here specifically are going to be these in most cases. A change in temperature, which is what most people think of when they think of state changes, but also a change in pressure. By increasing or lowering the pressure, we can cause state changes to occur as well. Turns out, as I mentioned earlier, there are 6 possible state changes that can occur. Most people, when they think of state changes, think of these two down here, the concept of boiling, melting, and in fact, our temperature scale in Celsius is based off of the boiling, melting point of water. What we're about to find out, though, is that those values are actually a little bit arbitrary in the sense that there is no one boiling point and no one melting point of water. They're actually dependent on a couple other characteristics. This brings us then to the idea of a phase diagram. And as you recall from before, a phase diagram is a graph that shows us all the different state changes that occur as related to the pressure of your sample and the temperature of your sample. Now we can look at this very simply, and we can take a look here at a pressure of 1 atmosphere, which is the normal atmospheric pressure on our planet. We can trace across this line here and see here we have the intersection between ice and water. This would be melting going across here, and we can see that this happens down here at 0 degrees Celsius. And we can trace further along to get to this line, which is the intersection between water and water vapor, and we can see that this change, boiling, happens at 100 degrees Celsius. And we can see the normal melting point and the normal boiling point for water. But these changes are represented by lines, and as a result, what we can see is that if we increase or decrease the pressure, those melting and boiling points increase and decrease as well. They happen at higher and lower temperatures. We think of melting and boiling as happening at the same temperatures because we typically don't change atmospheric pressure, but we can see clearly from this graph that when that pressure is changed, the actual values for these boiling points and melting points change as well. Now we can also use this graph to identify the different possible state changes that occur. For example, we can go from an solid ice to water, and this is something we'd be comfortable with. This would be melting. And we can go from water over here to vapor, and we can describe this as boiling. Those are ones we know. We can do these in reverse, going from water back to ice would be freezing, again one that people are pretty comfortable with. And going from gas back to liquid is where we start getting ones that people are less familiar with. This is known as condensation. This happens obviously in the summertime. You got your cold beverage in front of you. It's a humid day out and you can see little water droplets forming on the outside of your glass. That is the water dissolved in the air, turning back into liquid from the gas state, and they're condensing on the surface of your glass. Now, here's where things start to get a little stranger. Down here on the graph, once we get below 0.006 atmospheres, we see that there is no liquid state between our solid and our gas. We can go directly from solid to gas at low pressures through a process known as sublimation. And we can go from a gas directly to a solid through a second process known as deposition, where we basically have gaseous particles depositing themselves as solids directly without going through the liquid state. These are not state changes that we see happening very commonly, because again, they either happen with uncommon substances or they happen at pressures that we're not normally accustomed to working with. But these would constitute our last two of our 6 state changes. Last but not least, before we put some definitions down, it's important to note on our graph that we have some key points here. We have this point right here known as our triple point, and this point up here known as our critical point. And these are 2 temperature pressure combinations where some special stuff happens in our graph, and we'll talk about those in a second. So let's see if we can't jot down some basic information about phase diagrams themselves. What we've already pointed out is the fact that temperature of a state change are pressure dependent, meaning a boiling point is not a fixed thing, it's a fixed thing only at a specific pressure, and if you change the pressure, you're going to change the boiling point as well. If you've ever read the back of a macaroni box when it talks about making your macaroni in Colorado versus anywhere else, Colorado is at a high altitude, the pressure is much lower at those high altitudes, and as a result the boiling point of water is much lower as well. You've got to cook the pasta for a longer period of time to get it finished and done than you would here in Boston. We can talk about the graph a little more. When you find that your pressure and temperature is on the actual line, meaning it's on one of the lines separating our different things, what ends up happening here is a couple things. Both states are present. So for example, we're in the solid liquid line, you end up getting liquid water and solid water at the same time. This is the process of melting, and we talked about the fact that this is something that happens very often. You can't go past the melting point until everything has melted. And what's also interesting in this scenario, if you keep your temperature here, both state changes occur simultaneously. It means your liquid is freezing and your solid is melting, and you kind of get this cycling back and forth. Even more interesting, on the line is very common. At the triple point is a little stranger. If you notice, this is the intersection of all 3 lines, meaning all 3 states of matter are currently present, solid, liquid, and gas, and all 6 of our state changes are occurring. Solids are turning into gases, gases are turning into liquids, liquids are turning back into solids, and there's this constant flux back and forth. This is actually something that's relatively challenging to do because it's a very sensitive process, but when you do get it right, you get some interesting chemistry going along here. And we can kind of see over on the side, we have a quick picture of what that would actually look like. We see the solid very clearly, we see the liquid in the bottle. Unfortunately, the gaseous water vapor is something we can't necessarily see. To wrap this up, we got one more quick picture here of a phase diagram. Over on the left, this is a phase diagram for a different substance. Our previous one was water. In this case, this is a phase diagram for the substance carbon dioxide. You'll notice the general shape is approximately the same. It's the same kind of layout. The only thing that's different here is the temperatures and pressures where everything happens. For example, at 1 atmosphere, our normal pressure, when we trace across here looking for things like boiling points and melting points, we don't find those things. We find that the solid, the intersection here, is actually the sublimation change at normal atmospheric pressure, which means it goes directly from a solid to a gas. And if you think about CO2, when CO2 is frozen, we refer to it as dry ice. And the reason we call it dry ice is because when dry ice melts, quote unquote, it goes directly from the solid state to the gas. There's no liquid formed in the process, hence the term dry. Now we know now that dry CO2 isn't melting, it is sublimating, and it's going directly into that gaseous state. We can clearly see from here that we would have to increase the pressure quite significantly to end up getting liquid carbon dioxide as opposed to the solid or gaseous carbon dioxide. Now, just to give you a quick picture of what's going on here, over on the right side of the screen, we've got a couple quick videos playing here. In the top, we can see the process of a solid going to a liquid. This is what we saw from before. All of this is happening at atmospheric pressure. Because water changed from solid to liquid at atmospheric pressure, at 1 atmosphere, we get the melting state change. In the bottom picture, we see a picture of dry ice going directly from solid to gas. This also is happening at 1 atmosphere in pressure, but in this case, we're seeing the sublimation process because of the different locations of the critical point and the triple point of the two substances. We end up getting two different types of state changes happening under the same conditions. So that pretty much brings us to the end. What you should be able to do now, based on what we've covered in the video, you should be able to define the 4 states of matter. You should be able to compare them property-wise, and you also should be able to compare them at the atomic level. How do they look and behave differently? You should be able to define, but maybe not do too much yet, the concepts of intra and intermolecular forces. And then finally, you should be familiar with the concept of a phase diagram. You should know all 6 of the state changes that occur during a phase diagram, and you should be able to describe the graph itself. In class, we're going to spend more time with phase diagrams and talk about how you can use them to predict what will happen to a substance if we change, for example, pressure and temperature. But that's something, like I said, we'll cover more in class.